Good afternoon, everybody. My name is Bob Knight. I'm a principal system software engineer at NVIDIA, and my co-speaker is John Stone from the University of Illinois. Today we're going to talk about optimizing HPC visualization, simulation and visualization code using the new NVIDIA Nsight Systems tool. Nsight Systems is a system-wide performance analysis tool that's designed to focus directly on an application's algorithm. This tool helps you scale your algorithm across all the CPUs and GPUs on the system, whether that's a laptop or a DGX. Some tools focus directly on the CPU or maybe the GPU, but this tool is focused directly on your application's algorithm. It's going to help you find bottlenecks in your application. It's going to help you understand the cause of those bottlenecks, and then it's going to help you identify the right optimization to apply. So I'm really excited. John is going to share with us how he used Nsight Systems to optimize the visual molecular dynamics application, and he achieved a really impressive speed up. So Nsight Systems is part of the Nsight product family of performance tools. Nsight Systems is the first tool you're going to want to use as you start to look at the performance of your application. And as you eliminate the bubbles in your timeline and you start to optimize your algorithm, you're going to get to the point where the next most appropriate optimization is to tune a CUDA kernel or maybe a graphics shader. And at that point, you're going to want to switch to the Nsight Computer Insight Graphics tool. These are multi-pass profilers. They're going to give you a deep insight into those components of your algorithm. And when you finish optimizing those aspects of your application, you're going to want to return to Nsight Systems because tuning is iterative, and you're going to want to understand how your profile has changed and how it's shifted on the system. So, have you ever gone to an orchestra concert? If you arrive early, you might get to see the conductor warming up the musicians. And as they're warming up, he may stop them and point at one of them and say, hey, you're a little off tone, or your rhythm's a little off. And then they may continue, and he may stop somebody else and do the same thing. When you're an Nsight Systems user, you're kind of like that conductor. You're examining your application's execution across the system, and you're trying to understand exactly what it's doing, and you can see those things that are not quite as efficient as they could be. And you're going to understand what's the right optimization to apply. So you're going to want to use this tool to maximize your GPU investment. And it's going to help you to balance that workload across the system. You might be trying to achieve a real-time performance. You might be trying to achieve minimum time to solution when you're working in an HPC environment because you're sharing those resources. Or if you're operating in the cloud, you want to just minimize your cost of renting those hardware resources. So let's get into some details about the tool itself. So there's 3 different features of Nsight Systems that really helps you to understand your algorithm. The first one is when you utilize the NVIDIA Tools Extension API to instrument your application, then Nsight Systems is going to allow you to see that algorithm as it gets correlated with the rest of the tool's information. It's very important, and John's going to give you a great example of that. Nsight Systems also traces several different APIs, including CUDA, OpenGL, cuDNN, cuBLAS, and even the system APIs like pthread API or FileIO, so you can understand why your OS threads are paused, what they're doing, and what's going on. Nsight Systems captures backtraces in 2 different ways. It uses traditional sampling, but also can capture a backtrace when a thread becomes blocked, and will help you to understand why your threads are in that situation. Okay, so I've talked a little bit about understanding your application's algorithm. And from this screenshot, you can see we've zoomed out, and we're looking at the visual molecular dynamics algorithm. And from the different NVTX tags, you can directly see the 4 different phases of this application. And John's going to talk a lot more about this, but this is kind of a preview of what he's got coming up. Another thing that's interesting about Nsight Systems, and I don't think any other tool can do this, is the ability to correlate between an API and activity on the GPU. So when that API executes on your OS thread, you can figure out exactly when it starts to execute on the GPU. And when you click on one of those boxes that's representing the API or the activity, either one, both of those boxes become highlighted in a teal blue, and you can figure out the latency in between them and that cause and effect activity. Nsight Systems provides blocked state backtrace. And what I'm talking about is when a thread makes a syscall. So it's going into the kernel, and it's going to have, maybe it's asking for some hardware assistance, and it has to wait until that comes back. If you place your cursor on the thread state timeline, a tooltip will come up and show you the sequence of calls that led you there. So this helps you to understand how I got to this point in time. And that's very important when you're trying to understand what's going on and what's causing things to slow down. There's two different modes of collecting data. One, you can use a GUI, and you can have a host target setup. So you can use one computer to profile another computer, whether that's in your office or it's across the street. And then you can use the command line interface. This is really important when you're on a supercomputer. You're behind 3 different firewalls, and you're trying to get access to that thing, and you need to script that collection so it runs overnight. It's also really useful inside of a Docker. So I'm going to switch gears on you. I'm going to show you a live demo of navigating a report. And I want you to notice a couple things. First, notice the responsiveness of this UI. It's very quick to zoom in and out and move around on the timeline. The other thing is you can get into a deep level of detail. You can get down into the nanosecond level of understanding what's going on. There's 4 core areas I'm going to show you. One is again, we're going to see how that algorithm looks using NVTX API. We're going to look at OS threads and how they are represented as they trace through the different APIs. I'm going to demonstrate that correlation of OS API and GPU activity, and then finally, I'm going to show you how we use sampling to identify hotspots in the OS threads and what that looks like. Okay, great. What I'm going to do is I'm going to share 2 different reports with you. The first report was collected on my workstation. This is a 12 logical processor, single GPU workstation. And I was profiling a CUDA toolkit example called smoke particles. Smoke particles is just renders a smoke cloud as it floats above the floor. And what I want you to notice, so this is the first screen that you're going to see. And I've gone in and instrumented this application with NVTX tags to indicate when each frame was processed. So this row right here shows you the frame processing activity of the app. Each 10 frames is in a different color. I also added a busy loop into the frame processing code that increases in intensity every 40 frames. So when you get up to frame 38, 39, 40, it becomes very, very intense and takes a lot of time, and then it resets. So you can see the yellow frames are when this becomes very fast, and then again, we have 40 more frames, and then the blue frames. Okay, so we can see that this is 12 logical processors, and this is how the different CPUs were utilized during the collection. And now I'm going to open what's going on the GPU. This is a Quadro GPU 100, and we have a couple of different timelines showing memory activity and kernel activity. So on the memory activity, you can see is the red dots is all the different memory operations, and the blue dots are the CUDA kernels executing. So here we have some host-to-device mem copies, host-to-array mem copies, and 4 different kernels are operating in this workload. So what I'm going to do now is I'm going to hold down my control key, and I'm going to zoom in on one of these frames that took a long time. And you can see I can zoom in very quickly to get into low levels of detail. So the first thing I'm going to show you is this correlation feature that I've talked a little bit about. And on the CUDA timeline right here, we can see that the memory operations are in red. And when I click on one of them, you can see down here that this memory operation down here on the GPU becomes highlighted in teal. Blue represents CUDA launches. So when I click on this one, you can see down here, this is the corresponding launch. And with my mouse, I can drag over here, and from there I can see the amount of time it took to get there. So you can see the latency was about 117 microseconds. So you can use that feature to measure different aspects of your workload. I'm going to switch and look at this system timeline up here. And here we can see the syscalls and different system APIs that we were utilizing during the collection. Here we did an fopen, fgetString, fclose, and so on. And if I put my cursor up here on the thread timeline, you can see this tooltip that pops up, and it's giving us that block state backtrace. And we can see how we got to this ioctl call. Okay. Okay, so now I'm going to zoom out again a little bit, and I want you to notice that this render MVTX tag shows that it took about 3.7 milliseconds. And to run at 60 frames per second, we need to run at 16.6 milliseconds. Clearly, this frame running at 290 milliseconds is something's wrong with it, and we need to figure that out. So I'm going to double-click on this frame, and the screen resizes to the frame size. And I want you to notice down here at the bottom is the sampling data. Here is the sampling data for the whole collection, and here's my busy loop, the Fibonacci code, and it took about 69% of the time. When I drag my cursor across this long frame and stop, what I'm going to do is I'm going to filter in and pick just the samples that occurred during the time I dragged across. And by filtering in, you can see that this Fibonacci code now is 100% of the time. And if I right-click, I can get a call stack or a backtrace of what happened. And as you know, Fibonacci is recursive. It's a great busy loop. And we can see that this came from the display function, which is the main frame processing loop. So even though this is very contrived, you can see how this feature helps you to find that hot code that's running on your OSs and might be starving your GPUs from getting real work done. Okay, I'm going to switch now to a more realistic example. This was the Caffe 2 deep learning framework running on a DGX. You can see that we had 80 logical processors and 43 different threads. This is a Python-based workload. And we come down here to the bottom, you can see we had 8 GPUs running. And you can see right away that the GPUs are much, much busier than they were with smoke particles. By putting my cursor down here, I can see that they were, at this point in time, 86% utilized on this certain GPU. We had CUDA kernels running. So what I'm going to do is I'm going to zoom in again. And I want to draw your attention to this thread 908 that's running, that was tracing CUDA, cuDNN, and cuBLAS. And we're going to zoom in. And a couple things I want you to notice. Notice these big gaps here in the GPU timelines. These are opportunities. These are opportunities to fill your GPUs with more work and optimize this workload in a way that allows the GPUs to be more utilized. Now I'm going to go ahead and zoom in on some of these gory details and show you that we can get down into really low levels of detail really quickly. So here I've highlighted this CUDA setup argument call, and it's at the 140 nanosecond level. So you can see we can get in and out of this timeline really quickly with this GUI. And the level of detail is terrific. Okay, I'm going to switch back to the slides now. Okay. So as John goes through his explanation of how he used the tool, he's going to run across a lot of different optimization opportunities. And these are some of the things that you can find with this tool. You're going to see things like thread synchronization, where threads are causing, or the synchronization algorithm is causing threads to slow down. You're going to find things like hot code in your CPU with sampling, and when you're operating on a single GPU, you might have memory operations that are blocking or serializing your GPU, or just unnecessary altogether. Sometimes there's unnecessary synchronization. You might do a device synchronization when you could have done stream synchronization. And these are different things that you're going to find really quickly that you don't think about when you're coding this up. Or maybe you have multiple programmers that are working on this, and they're not sure what each other is doing, so they take the conservative route and add more things than they need. Sometimes you're going to see CPU and GPU overlap, where they're doing a lot of communication that's unnecessary. And when you're operating in a multi-GPU environment, you want to make sure your communications are clean and that you're utilizing streams to overlap memory operations and kernel execution. So John, I'm going to let you take over.
Thank you. All right. So my day job is I develop a tool called VMD. VMD is a molecular visualization and analysis tool. And today I'm going to show you how we used Nsight systems to optimize one of the new algorithms that we recently added to VMD. One of the things that VMD gets used for a lot is to take experimental atomic structure data and prepare that data for use in various types of simulations, be they molecular dynamics or lattice microbe simulations. And one of the steps in doing that that's particularly time-consuming and very effort-intensive for a scientist is taking a cryo-electron microscope image, like the one you see sort of on the left, that might be a tomogram or a density map, and labeling the different parts of that structure with different information, basically determining what kinds of structure those pieces are, assigning them different indices and so on. And then once those things have been labeled, they can be used for visualization, or we can use that to help us build models. And I'll tell you a little bit about how that's used for lattice microbes, which is sort of the lattice-based model you see on the far right. So in terms of what I talk about today, it's not really that important that you understand how image segmentation works. It's really just an example here. So when you watch what I show you, just think about how these optimization opportunities relate to your own code. It's not critically important that you follow any of the details of what I'm doing, because what really matters to you is how you would apply this tool to your own algorithm. So for my own case, one of my goals is to reach interactive performance. We want to improve the performance of this image segmentation tool to the point that it is interactive in the range of a second or less. And ideally, we would like it to be fast enough that a user could vary various segmentation parameters with a GUI and have it immediately recalculate these things in an interactive fashion for sort of the normal size problems. And then for sort of next generation problems, we want these things to be fast enough that they can be done in, say, a minute. So that's where we stand. If we begin using Nsight systems on a program like VMD, if you do no work and you just run the tool inside of Nsight systems and you watch what it collects, you'll get a timeline like this. And if I just describe what you're seeing here, this is just a straight run of VMD looking at some of the CPU threads and the GPU activity for a simple image segmentation test run. Now, with no labeling, you can't really tell what any of these things are yet, but of course, myself as the programmer, I know what I'm seeing just because I can recognize the different phases of an algorithm. But what we care about initially is just looking at how well is that GPU used. Well, there's an initialization phase here where it's not really doing much, and maybe that's fine. Here is where I can see one of my algorithm phases is really starting to hit the GPU, and it looks moderately okay. It's at least using the GPU, right? And then on the right-hand side, we can see that there is this sporadic activity bouncing back and forth between the GPU being utilized and a bunch of memory copy activity, which you see down on the bottom as red. And just looking at that, the first time I loaded this up, I said, what is going on there? That is not supposed to be happening. And this is something, you know, I developed this code. My colleague, Brendan McMorrow, and I developed this together, and we worked on different parts of the code. And we were getting a very good GPU speed up, we thought, initially, and so this was just going to take it to the next level. But when I saw that, I realized there was a huge opportunity there to make this code faster. So one of the things you can do then to make it easier to use Nsight systems with your code is to annotate different phases of your calculation with little tags. And so there's a little header file that comes with the CUDA toolkit that basically gives you functions that you can call that will add your own annotations to the code. And you can see that by labeling these different things, we can see when the program is entering and leaving different phases. We can label different things from an algorithmic level, or even in my case, I added tags to the scripting language in VMD, so I can even, throughout a complicated science script, I could use the same tool to analyze what a scientist is doing with a self-written script. And you can see these little time bars then have the runtime associated with each of those things. Vertically stacked bars here then show the components of where that runtime is going. And as I added more detailed tags, then you can see more and more about what's going on. So once I zoom in on, let's say, just the segmentation part of the algorithm, I don't need to see the VMD startup time or when it's initializing all the GPUs or compiling shaders. Right now, we just care about the segmentation algorithm. So I'll double click on this yellow bar, which is my test script. And that zooms it in, and I can then see all the runtime that's associated with the different steps underneath. And this is the original code, not optimized. This is just where we started. And I can again see all these different phases of my algorithm. I can see there's this latter half that's iterative that has a whole bunch of those undesirable memory copies. And I can see other phases where I've got things on the CPU or where I'm doing disk I/O or other things. And this is going to be our reference then. So we're starting from here, and we're going to then drill down with the profiler and sort of determine what our problems are. Again, down at the bottom of the screen, you can see the GPU activity shown in blue here when the compute side is active, and the red showing where there are those undesirable copies. So if we drill into this a little further, now I've circled sort of the things that immediately stand out. As a programmer, knowing how this watershed segmentation algorithm is supposed to work, I noted two things right off the bat. One was all of those excess memory copies. That's probably the worst thing I saw. And then the second most surprising thing I saw was that this first phase of the algorithm is sort of the watershed phase, and the last phase is a merge phase where we take a bunch of segments and merge them together. In that first phase, we're spending a whole bunch of time on a CPU kernel that just builds the data structures that the GPU is going to use. And that wouldn't be so bad, but it's about 30% of the entire runtime of that entire phase. So that's not very good. So we've got to do something about both of those things. If we zoom in much further, looking at that latter phase where we are merging these segments together, we can now very clearly see we have this alternating pattern of the GPU being busy and then going idle while these memory copies are going on. So I know that these memory copies don't belong here at all. And this is just a one-line mistake in a class interface. You have a complicated algorithm that's got 10 different classes in it, and one of the classes just doesn't realize that there's no necessity to do a host device transfer, and it did it just eagerly. So we fix that, and then we get those to go away. So by removing just, fixing one or two lines of code, we have already sped up this entire algorithm here by a factor of 1.4. And now if you look down at the bottom, those big gaps between the kernel executions are now gone, and the memory copy time is much smaller. If we then look closely again, zoomed in, you can see now those big gaps that we saw before are mostly collapsed. You can see a few little red dots here, but it doesn't look so bad. This is starting to look pretty good. And the speed up for just this phase of the algorithm is 1.7. So we've taken it, the overall runtime was 3 seconds, and this part was about 2 seconds, and now it's only 1.2 seconds for this green bar here. So then we notice we have this watershed phase. We run a watershed algorithm as the front end of this image segmentation, and out of about 900 milliseconds, let's say, 310 of those are just the CPU initialization function. Well, that's clearly not what we want. That's taking about 30% of the overall runtime. And you can see that while that's going on, the GPU is doing nothing. So we're getting no speed up out of that at all. So I then wrote a GPU kernel to do this. Why not have the GPU initialize itself, build all of its own data structures? It was very tricky. But doing that, we go from 300 milliseconds down to 13. So that's what we want, and that's about 23 times faster, and we've crushed that runtime from 900 milliseconds down to about 600. So that's pretty good. So we have already got now a 1.6x overall speed up, and we're making good progress. So now, the pattern here is we're looking for things that are taking either, identifying bugs or deficiencies like the two that I just pointed out. Once we get past the things that are sort of wrong, then the next thing is to observe Amdahl's law and realize that our greatest speed up opportunities are the things that represent the largest fraction of the remaining runtime. And so one of the things that remains then, digging into the latter half of the algorithm where we have a large number of successive iterations. We have a scale space filter, and it's doing some things to find maximum voxel intensities and things like this among different segment groups. And there is one kernel, this find groups max index, that takes almost 10 times as long to run as the other kernels that do things like Gaussian blurs and other steps of the algorithm. So this is clearly our next target. We want to make this as fast as we can, and this will have the biggest impact on our overall runtime of any of the kernels that are sitting there. So this is an opportunity for us to basically say, okay, well, that's a kernel optimization opportunity. We identified the opportunity with Nsight systems, but now we might run Nsight Compute or NVVP or another tool to help us improve the performance of that particular kernel. In my case, that's what I did. And then I developed, instead of using that original kernel, I identified an opportunity to write a new kernel that did atomic memory operations to shared memory rather than global memory, which you can do as the problem size decreases as the iterations progress. And once the problem size is below a certain threshold, we can start using shared memory for doing some parallel reductions instead of doing those things in global memory. And so the later phases, later iterations of the algorithm then run substantially faster. And so by doing that then and having 4 versions of this kernel, I think give or take 4 versions, we now have a total speed up of over that original kernel of about 3x on average. So that's pretty good. And our overall speed up for the whole algorithm is now approaching 3x also. So this is very good. Digging into this now, you can see after having done that optimization where we had been around 11 milliseconds, we're now down to 1.1 milliseconds. And this kernel is now as fast or faster than the nearby other algorithm steps. And so we can basically move on from there to look for other optimization opportunities. One of the things we do when we write new algorithms in VMD is we put a lot of safety checks everywhere in the code. VMD is a desktop application. It runs on machines that are competing with things like web browsers for finite GPU memory. So we have all kinds of error checking, especially early on when we're developing something new. But of course, this becomes a trade-off. Later on, when you've sort of determined where all the failure points are in the code and where you have to have things be bulletproof and where you can be a little leaner and meaner, then you have to go back and say, hey, I don't need all those error checking calls. And one of the reasons is those error checks, just to determine if you encountered an error with a CUDA mem copy or a kernel launch, you end up having to synchronize your streams and do a round trip back to the driver and get some error value back. Well, those things are fine if you do them infrequently, but if you do them a lot, they become sort of a barrier to the efficiency of your GPU execution. Now, right now, it's not a huge deal, but we're going to do a series of optimizations here where we want these things removed. And so we're going to basically eliminate these, and we can see that there are a lot of them just going on here among these different algorithm steps. And so we're going to eliminate all those, and having done that, now you can start to, instead of seeing 100 CUDA device synchronized calls, now you can actually see the other API calls that are allocating memory, freeing memory, copying things to device symbols and things like this. And this then opens up the door for our next optimizations. One of the things that's a problem in an iterative algorithm is, for programmer convenience, it's often nice to just allocate memory right before you need it, use it, run your kernel, and then free that memory. Well, that's great for programmer convenience, but it's not very good for performance. And you'll see that what happens is when you do things like memory allocations and deallocations, you're essentially log jamming the GPU. You're tying it up for a period of time while the kernel drivers and so on are manipulating the MMU virtual memory pages and all this and giving you access to certain areas of memory. While all that's going on, your GPU is essentially doing nothing. You have a big bubble in your execution here, and so we want to collapse that. And so the way to do that then is pre-allocate the memory buffers that we need for our work and then reuse them iteration after iteration many times. And that requires a little planning. After we do that, we can crush more of these API calls. So we're reducing API calls during the run, and we're getting rid of things that were spreading out that execution. So we're getting progressively higher GPU utilization as we make these optimizations. And again, even after we've done all those optimizations to our own code, it turns out there are also similar things going on inside of the library we were using. So we use Thrust to do parallel prefix sum. And because Thrust has an API that's meant to be similar to the behavior of the C++ standard template library, there are some complexities in how you do things like pre-allocation of work buffers and so on. There's a way to do that with Thrust if you're using a very recent C++ compiler. But the other alternative, and the one that I, in this case, chose to follow, is to replace the calls to Thrust with a call to another library called Cub. And Cub is basically another template library for doing parallel reductions on GPUs. And actually, Thrust uses it to do some of its device parallel prefix sum calculations. So one of the nice things about Cub is it has an explicit API for pre-allocating all of the work buffers you intend to use. You can basically call it, find out how big the buffer has to be, and then you can use that buffer over and over and over if you've pre-allocated. So having done that, then we get rid of all of those allocation and free calls, and then our execution stream looks much cleaner. Now we're down to things that are basically memory copies, kernel launches, and we're not doing any allocation or deallocation anymore, either in our code or in Cub. Having done that, now we have a better opportunity to overlap different API calls. So the steps up to this point, this algorithm has a very strict serial dependence on one step from one step to the next. So there isn't that much opportunity to overlap memory copies or kernel launches. So that's why it's a relatively simple example. But there is an opportunity to make better use of the CPU to enqueue work. You know, a GPU, you can start a memory copy asynchronously and begin enqueuing all of the kernel steps and other memory copies that follow it. And while the GPU is busily handling the first thing that you put in the work queue, you can be putting in the next things, and that frees up the CPU sooner to do other things, perhaps. And it just makes the CPU enqueue that work that much more efficiently. So we can just make a few changes and change our synchronous calls to async calls, and that gives us a nice little speed up. And then digging around for other low-hanging fruit, we discovered again there was a tiny little mistake in a constructor for one of our several classes, and it was doing one unnecessary memory copy. It didn't harm anything except for it made the code run slower, and so we didn't even notice that it was doing this. But this is another one of these things that Nsight systems can show you this stuff immediately. It's obvious in the profiler, even though I wouldn't have known that this was going on if you had just shown me timings or things like that. So just a couple of lines of code, we get rid of that extra copy, and now at the very end, we have a much more densely packed algorithm. The GPU is being utilized at about 97% utilization through both of these algorithm phases. And our total speed up, this is on the Pascal Quadro GP100, is about 3.2. So that's very exciting. What's even better is that speed up that we got on the Quadro with the Pascal generation, we get an even bigger speed up for Volta. And part of that is, you know, I went well into the weeds into these small optimizations. It probably didn't make that big of a difference on Pascal because Pascal had more work to do or it wasn't as powerful. But when you get to a GPU that's like twice as fast, these little small optimizations start to make a difference, and you're not as dependent on how fast your CPU is. So the better you do with eliminating all these overheads, the better your code will scale to faster GPUs. And so now at the end, we get to a point where on a Volta, this algorithm runs in 0.64 seconds, and it's about 12 times faster than the fastest tool that competes with our software that we're aware of. So now I'm going to show you another tool that we developed called Lattice Microbes. It's a tool that simulates cells using a lattice model. And so we take those tomograms that I described earlier, and after they've been segmented, they are used to create a lattice model of the same cell, and then the dynamics of that cell are then simulated by lattice microbes. And so it looks a little bit like you could say it looks like a Minecraft scene almost, but that's what the lattice model looks like. So inside lattice microbes, this is just like with other iterative simulation algorithms. It has a time step loop, and at every time step, every one of these grid cells, or these lattice sites, undergoes diffusion of particles and reactions between different particle species that occur at these lattice sites. And we have some bookkeeping to do to watch out for various boundary conditions and so on. And so this is what the major steps of the algorithm look like. Now, on a single GPU, you can see we have a certain amount of runtime. This is about 75 microseconds for a time step for a certain size cell model. One of the things we noticed, now this is this code has been developed over 10 years already, so we weren't expecting to find any significant problems, but one of the beauties about a tool like Nsight Systems is you can just see these things visually in a few seconds, and as a skilled programmer, you say, hey, wait a second, why do we have a stream synchronized right before a memory copy? And if the memory copy is done in the default stream, this is sort of implicitly synchronized, so we don't need to do that. So that then becomes an optimization opportunity. And by changing that code to do the little copy inside of the kernel, so we use a little trick where we use zero copy host mapped memory, and the kernel itself does its own writes to the host memory. Now we don't have to have that last extra memory copy, so we got rid of an API call, and the synchronization is still there. And so just doing that on this size problem gives it a 20% performance gain. That's great. That was a very exciting outcome. If we run lattice microbes on larger problems, we need much more horsepower, so we start using big multi-GPU systems. The time step loop looks similar to what you saw before, but now there are extra steps involving data exchanges, so the halo or boundary between the different GPUs has to be exchanged at every time step, and this makes a more communication-intensive algorithm, and we have to worry about things like synchronizing the activities of the different GPUs and CPUs. And so very early on, running on a multi-GPU system, here's an example where looking at the trace in Nsight Systems, you can see there's a green box that we've drawn around a vertical swath of the different GPUs and CPU threads. And you can see at this little red circle, there's a synchronization here, and there's a lag between when the early threads run and when the last one gets busy. And part of what's going on here is that this code was originally written using condition variables, and condition variables can have a much higher overhead than things like spin locks. And so by replacing that condition broadcast with spin locks, we can see there's a big improvement of these are basically histograms of the amount of time that this code took at that point in the code, which was determined. We basically collected this profile trace and then ground through it using a Python script to extract all of the latencies that all those spin locks had, or all these condition variables had, and now you can see what those histograms look like. So this is what it was in red, and having replaced that with a spin lock, this is what it is now. And so we want it basically collapsed over to the left-hand side. And so for this size problem, this is basically a 25% performance gain just by using a more efficient, performant synchronization primitive on the CPU side. So that's something that none of the existing profiling tools would have given us, and we can see that much more clearly here. Another thing that happens with multi-GPU runs, and when you have a stencil calculation like this, you have ragged edges and boundary handling to deal with. At the edges and where you do various copies, you may have non-contiguous memory copies going on. And so the sort of naive way of doing that is you just have a large number of small copies, but that's not very performant. What we would rather have is something where we collect all these and compact them down into a minimum number of transfers. And so having done that, replacing those individual transfers with a sort of a compaction operation that's built into the kernel, you can get 10 to 75% performance gain. And that's because you've gotten rid of all that overhead for launching a large number of small copies. And then lastly, I'll show you another one. So here's a case where we have improved the performance of the device-to-device transfers using peer-to-peer copies inside of the kernel. So this is written into the compute kernel itself. And by doing this on a large problem, which is on the left, you can see there are some small gaps there. There's not as much opportunity to improve that. You get about a 5% performance improvement. On the right-hand side, for a smaller size problem where we're more into the strong scaling regime, you can see the gaps are bigger. There's more potential opportunity to improve that, and by doing that peer-to-peer copy in the kernel, in this case, it's as much as 28% faster. So that's really cool. And you can see these things visually in the profiling tool.